On October 30th, 1961, the Soviet Union detonated the Tsar Bomba. It yielded 50 megatons of explosive force and punched a mushroom cloud 40 miles high into the Arctic sky. The blast was so intense that its shockwaves were recorded circling the Earth 3 separate times. For a fraction of a second, that single explosion released energy equivalent to 2% of the sun's total power output. Yet, as a practical weapon of war, this device was entirely useless. It weighed 27 metric tons. Delivering a payload that heavy required a heavily modified Tu-95 bomber, an aircraft far too slow to evade anti-aircraft defenses. The bomb even had to be dropped with a giant parachute, just to give the crew a 50-50 chance of flying far enough to survive the blast. You can build the largest explosive device in human history, but if the plane carrying it is shot down hundreds of miles from the target, the weapon's yield is 0. By the 1960s, the United States had established concentric rings of defense. Giant early warning radar stations could detect incoming aircraft from thousands of miles away, giving interceptor jets and surface-to-air missiles plenty of time to destroy a slow-moving bomber. Soviet military planners recognized this bottleneck. They realized that increasing the size of their bombs offered diminishing returns. They needed a delivery system that could bypass those radar networks completely. The focus shifted away from the raw power of the warhead. The new objective was mastering the physics of an invisible, unstoppable strike. Look at this globe. The United States Ballistic Missile Early Warning System, or BMOVS, was built to face north. Planners expected traditional intercontinental ballistic missiles to take the shortest route from the Soviet Union to North America, flying high in an arc straight over the North Pole. Soviet engineer Mikhail Yangel proposed a workaround. Instead of flying into the teeth of the northern radar wall, the Soviets would do the exact opposite, launching their missiles south. The weapons would travel under the Earth and approach the United States from the completely undefended South Pole. To do this, they created the Fractional Orbital Bombardment System, or FOBS. Rather than shooting a missile in a high, predictable suborbital arc, FOBS put the weapon into low Earth orbit. By maintaining an altitude of about 150 kilometers, the warhead stayed below the radar's line of sight. An ICBM approaching from the north would give the United States about 30 minutes to detect the launch and retaliate. A FOBS strike arriving from the south, hugging the atmosphere, effectively reduced that warning time to 0. Reaching orbit requires vastly more energy than simply shooting an object from one continent to another. A standard ballistic missile goes up and comes back down. A FOBS missile has to accelerate to orbital velocity, moving fast enough to continuously fall around the curvature of the Earth. Once in orbit, the weapon travels until it is nearly over the target. Then it performs a retrograde burn, firing its engines in reverse to slow down and drop out of orbit, sending the warhead down toward the surface before it completes a full revolution. Notice how much smaller the FOBS payload is on this scale comparison. Because so much of the rocket's capacity is consumed by the fuel needed to reach orbit and execute the deorbit burn, the actual nuclear warhead had to be drastically reduced in size and weight. The flight path also degraded the weapon's precision. Navigating into orbit, braking, and surviving a much longer, shallower atmospheric reentry meant a FOBS warhead was significantly less accurate than a standard ICBM. Western intelligence estimated the yield of the deployed FOBS warhead was between 1 and 3 megatons. That is a fraction of the 50 megaton Tsar Bomba test. But an inaccurate, low-yield warhead that detonates exactly when you want it to is devastating. A massive city killer that gets intercepted along the way is useless. By the early 1970s, the United States closed the southern back door. They deployed a network of space-based early warning satellites that looked down from orbit, capable of detecting the infrared heat plumes of missile launches, regardless of which direction they flew. Diplomatic efforts also sought to close the loophole. In 1979, U.S. President Jimmy Carter and Soviet leader Leonid Brezhnev signed the SALT II agreement, which explicitly prohibited the development, testing, and deployment of orbital nuclear weapons. The Soviet Union complied with the treaty's terms, decommissioning their FOBS installations in the early 1980s. They shifted their strategic focus to submarine-launched ballistic missiles, which offered short flight times and stealth capabilities by firing from the ocean depths. The original FOBS silos were razed, but the core military philosophy, the pursuit of a weapon that guarantees a strike by eliminating the enemy's warning time, became a permanent fixture of global military doctrine. In August 2021, the People's Republic of China tested a system that brought the orbital strike concept into the 21st century. They launched a rocket into orbital flight that deployed a hypersonic glide vehicle, a craft capable of maneuvering through the atmosphere at extreme speeds. Russia has also introduced the RS-28 Sarmat, a modern, liquid-fueled intercontinental ballistic missile with a range of up to 38,000 kilometers. Military analysts note that a missile with that much reach is theoretically capable of executing a THAAD's trajectory today. Meanwhile, the United States has focused on integrating low-yield tactical nuclear weapons into its arsenal, prioritizing weapons that are smaller, faster, and highly precise over the massive gravity bombs of the past. The ambition to build the most destructive single explosion died in the 1960s with the Tsar Bomba. The modern threat relies on physics and speed. A weapon stationed in orbit, capable of striking from any direction, means the impact arrives before the early warning alarms ever trigger.